Welcome, my dear students, for this new session. In the last class, we defined the composition of a two linear maps and show that the composition of a two linear maps again is a linear, and then we show that the composition of a two linear maps need not be commutative but associative, and also try some examples for we have to show that how to calculate the composition of a two maps. Composition of two maps is defined. Only we have to just say that the domain of the range of the first function is the same as a codomain of the domain of the second function is defined. So we also show that is means if not necessarily t is defined means st is also defined, and we have to just say that one is a properties, maybe both of them is not defined, and also find one of the property. We take a two non-zero linear transformations defined, and t of s is equal to 0 and st is not equal to 0. Okay, in this class we discuss some basic properties of composition of a linear map. We try to discuss this because we have to show that sum of a two linear transformation is a linear transformation. So now we have the distributive properties of a linear transformation. So we just try to these properties where for u, v, w and z are the vector spaces, and then t1, t2 we have defined from u to v, s from v to w, and we have a r is from the w to z. We have a three linear transformation is defined is there. Now I already show that this is a well defined. Now I have tried to in this by example we show that the associativity condition of a linear transformation is satisfied in the previous class, but now in this class I have to provide a proof of this. This is the distributive properties are here. Okay, so we start from the A part where for any t1, t2 are the linear map from u to v. So we have a u to v. We have a this is a t1. The t1 plus t2 is also t1 plus t2 is also from u to v, and v to w. This is s. Then clearly this is a u to v is a s composition. You can say that t1 plus t2 is a defined, and also you just take a u to v. We have a t1, and then v to w. You have a this is equal to again you have a s of t1. Similar fashion we can define from u to v, and then this is nothing but is equal to w as this is t2 map, and then we have again this map is a s of t1. So s of t1 and s of t2 is defined, and now clearly s of t1. So we have s of t1 from u to v, and s of t2 are from u to v, and these two are linear maps. So we can say that this implies that we can say that s t1 plus s t2 is also from u to v is a linear map, and then clearly we show that this again u to v. So again u to v, and then we have to show that this map is a s times of a t1 plus t2 is also from u to v. So that means this both sides of a are the meaningful, and now we try to prove that these are the equal to the same. So we take any arbitrary element is well defined because of the diagram. We can easily say that this is the also u to vw, and this is the both the maps are clearly is well defined. Now both sides a are the meaningful. So now we have to take any arbitrary element for u in u, and then we have to try to check into this form. So as composition T, by that using the composition T. So this can be because T is a linear map. So this can be written by the sum of a two linear maps can be defined in the form. So we use the sum of a two linear maps conditions. So this is we already show that if T1 T2 are a linear map, then sum of a two linear map is again linear, and then it's defined in the form of a T plus T1 plus T2. U can be defined as a T1 U plus T2U. So this can be by using this sum of a two linear maps conditions. So I can say that this can be written in the form of a T1U T2U, and now again because S is a linear map, S is a linear, so S of U1 plus U2 is this which can be, because S is a map from V to you have a W, and then you have a this T1 plus T2 is a map from, again you have a U to V. So T1 plus T2 you have a map from U to V. So now you see this clearly here is a element of a, this is equal to T1 plus T2 U is the element of a V, and this is element of a S. So this using the S, these are the vector spaces, and then we can say that this by the vector spaces, this is using the linearity of a S. So this can be written S times T1 of a U plus S times T2 of a U. And now by the using the definition of a composition map, this can be written as ST1 U1 plus ST2 U2, and also this can be written as a ST1 plus ST2 over U. And because the result is true for all U belongs to the U, then we can write S of T1 plus T2 is the same as S of T1 plus S of T2. So this complete the proof of the this result. And now second result is we have a S1 S2 T. So we just take a this is clearly by the, I just prove this is in this form. So we have to show that this is a S times of a T1 T2 is the this form. Now second part is S1 plus S2, and then you have a T. This is nothing but is equal to S1 T plus, yeah, we have a T1 or T2, whatever is, I just check. This is equal to T, okay, T from U to V, or T1 is not a problem. This is T from U to V, S from V to W, S1 and S2 V also. Then sum is S1 plus S2 also V to W. So we have to put S1 T1, we take a T1 and T1, then S2 T2. So this is element for sum is element for T from U to V. So this we can say that S1 plus S2, now T1, and then we have to take a sum of the element of a T over U, can be written as a S1 plus S2 T of U. And now by the use the sum of a linear map condition of a definition of a this, we have to just S1 plus S2 of a U can be written as a S1 U plus S2 U. So by this condition we can say that S1 of a T of U plus S2 of T of U, and again by the composition map S1 T1, okay, T1 S1 T1 over U, S2 T1 over U, and this again by the condition S1 T1 plus S2 T1 over U. Result is true for all U belongs to U. This implies that we can say that S1 plus S2 T1 is the same as a S1 T1 plus S2 T1, and we say that this complete the proof of the B part. Okay, now we come to the associativity conditions. We try to solve this into this form. We starting from the right hand side RTST. So we using the condition of a this can be written R times of a, you have a S of a, again by the conditions we can write into a this form. So this can be written as a RS of a TU by the definition of a S composition T, and this can be written in the form of a RS over T of a U, and then we can say that R composition S over by the definition of a this. Okay, this is RS over T of U, and now we can just say that this can be written as a RS T over U, and this is result is true for all U belongs to U. This implies that R of S T is equal to, we can say that R of S and T. So this means R of T is equal to this thing. For all U, this is equal to this. So we have to prove that R of S T is the same as a RS or T. So now this complete the proof of this the third part of this. Now we have to take a alpha 1, and then we can check is this form. So alpha times s of tu is equal to alpha time. Now using the composition, again we have to just say that into this form, and now we have to taking into this form. This complete the proof of this thing. So now this complete the proof of the this complete theorem. Okay, now we just take one more result. Is this if we have a t from u to v is a linear transformation. So we have a u to v is a linear transformation. This is t, and then you have a this is equal to v to v. We have a identity of a v. Then we have a identity of a v comma t is a map from u to v, and this is nothing but is equal to t. So identity of a v comma t is the same as a t. So we get identity of a v t into is equal to as a t. And also if we have a we define as a u to u is a identity of a u, and then u to v we have to define as a t, then u to v we have to define as a t times of a identity of a u. So if we have identity of a u, again we have a getting is equal to t. So this is a very important questions composition of a two linear with the identity transformation. So I just take a when operating in the left side and operating in the right side with identity of a vector space V, and here identity of a vector space of a over U. So this means this can clearly be transformed, leaves any linear unchanged. Means we have to prove this is very clearly. We have to show that identity of U is equal to T. So by the figure, this is clearly this is satisfied. By this, we can say that this is u to v. Then it is nothing but is equal to t, and also u to v. Again, nothing is equal to t. Now we have to prove this by using this. So u be any arbitrary map, then computation t of I of u. So we just say that t of I of u comma u. This can be a t of we have a identity u of a u. Now you know that identity from u to u means I of u is equal to u. This is nothing but is equal to t of u, and this is results true for all u belongs to u. This implies that t of identity of a u is equal to t. And now another way we have to just say that identity of v and t over we just take a u. Then we can say that by the composition definition of a composition of a map t of u. Now identity of we have a v is a map from v to v, and then any v identity of a v over v is equal to we have a v, and t is a map from u to v. If u is the element of a u, then clearly t of u is the element of a v. So this t of u is the element of a v. So this can be written as a t of u by the definition of a identity composition. And then we can say that this again for true for all u belongs to u. So we can say that identity of a v is equal to you have a t, and this complete the proof of these two identity. I use this identity in later of discussion, and now I just complete the proof of this thing, and see the identity transformation behaves as expected under the composition. Okay, now we have to just this is a very interesting theorem which by motivated by this identity transformation. I take a we have to term some we take a this map is a non-singular, t from u to v is a non-singular. This means non-singular means this is a t is 1 1 and onto. So what is saying that if a linear map t from u to v is a non-singular, if and only if there exists a linear map S such that t of S is equal to v and S of t is equal to u, and in such cases S is equal to t inverse, because if we have to just take S as a we take a t of inverse, so then we can say that t inverse and S is equal to t inverse. We have to write in the form of a this can be written as a t of a t inverse, and we have a t inverse t. By the previous example we can just say that the theorem we just take. So I just try to prove this, and this is assuming that t is a non-singular. So if t is a non-singular means t is 1 1 and on 2. So we just take a t is a non-singular map. So t is 1 1 and on 2 map. Now we have to just t is onto, because t is onto, for every v belongs to v, there exists a u belongs to u such that t of u is equal to v. Now suppose we have to assuming that there exists a, because t is 1 1, and that means this t is 1 1, so this u is unique. So we have, this is very important part, because if t is by the ontoness of a t, we can say that v belongs to v, at least one u belongs to u, and this one belongs to u is a unique element, u belongs to u, where t of u is equal to v, because the t is giving you a 1 to 1. Now we have to define another map as from v to v by s of v is equal to u, where t of u is equal to v. Now we try to find the, we have to just say that s of t. Now we have to find this two map ts and st. So we just try to ts first. We have a t of s. Now s we have to just check. We have a u to v, we have a 2, we have to just take a v to u, we have a s, and then u to v, we have a is a t, then we have a u to v is equal to, we have a t of s. So this is v to v, so this means t of s some v is equal to t of s of v. Now s of v is equal to u, so t of u, and t of u is equal to, you have a v, v is nothing but is equal to identity v of a v. Then we can say that for all v belongs to v, this can be written as a t of s is equal to, you have a identity of a v. So this means we can say that we have to t of s is equal to identity of a v, we have to prove this. So this is identity of a, this is nothing but we can say that this is t of s means as t of s is equal to identity of a v. Now we try to find the another way also, identity of s st. For st we just take a we have a t from u to v, then s is equal to, you have a v to u, this is as, this is, you have a st. So st of a u, so we just take a st some element of a u, can be written as a s times of a t of a u, and now t of u, you have a v, this can be written as s of a v. Now s of v we have to define as a v u, and this is defined as a u, so this is u, this can be written as a identity of a u into u. Now this is true for all u belongs to u, so this can, we can say that simply we can say that st is equal to identity of a u. Okay, so this means we can say that prove both the condition. If we have a t is a onto map, then we can say that 1 1 and onto, then st is equal to identity of a u, and ts is also identity of a v by this, or we can prove this part as a previous result. We can just, where we can say that t of we just say that sorry, this one we can just say that this is a by this I of t is equal to t, I of t, this is t of, okay, so this is complete. We can also, this is t of I of u is equal to t, and I of vt is equal to also t, and in place of this we take a t inverse. For this we can just say that by this there as st, we can say that s of t is equal to identity of a u, and then we have a, this is equal to v, and then s as a, s can be written as a t inverse, so we can just satisfy this condition also. Okay, now we have to just the conversely part of this. So conversely we have a there exists this condition is giving st is equal to identity of u, and ts is equal to identity of a v. When we show that this is a t is a non singular, this implies that we show that t is 1 1. So t is 1 1 means t is a map from u to v. So we take any element u belongs to the kernel of a T, and then we show that if the kernel of a T is equal to 0 subspace, then we can say that this is clearly is satisfied. So U is the element of a, this means T of U is equal to 0. So T of U is equal to 0. We have to satisfy clearly T of U is equal to 0. So we just say that by this we can clearly show that T of 0 is equal to 0, but we have St of U can be written in the form of this thing. So we can, this is St of a U is equal to 0. Why this is 0? We just say that clearly S times of a we have a T of U, T of A is 0, as 0, S of 0 is always equal to 0. So but this St is equal to what? Is the identity of a U. So this means identity of a U is always U. So this means we can say that S of T of U is equal to the identity of a U, and identity of U is equal to U, but St of a U is equal to, you have a 0, and St of a U is equal to U. So this implies that you have a U is equal to 0, and if U is equal to 0, that means we can say that kernel of a T is equal to, you have a 0 subspace. This implies that T is 1 1. So this completes the first part of this using this condition. Now we show that T is onto. If T is onto, means we can say that range of a T is equal to same. So for take a V belongs to the V, and then we have a T of SV is equal to V, because T of SV T of S is equal to identity of a V is equal to V. So we can show that Ts over V is equal to V. So therefore there exists an element U is equal to S of V in U. T of U is equal to V, hence T is a onto. So this is clearly T is onto. This means we can say that this T is we can say thus this is thus T is a non-singular, and therefore if T is a non-singular, then T inverse is exists. So we can say that if T is a non-singular, then clearly T inverse exists. So now if T inverse exists means sorry okay, so that means by this condition we can say that thus T is a non-singular. If T is a non-singular, then we have to prove that if T is a non-singular, then inverse T inverse exists. If T inverse exists means T inverse can be written in the form of a T inverse of a identity of a V. Again, because we can just say that identity of a V, this is, we have to say that T of I of V is equal to T. So this means T inverse of I of V is equal to, we can say that is equal to T of this. So I of V is nothing but is equal to, we have a T of S, then T inverse T is equal to S of V. T inverse T is equal to identity of a U, and U of S is equal to S. So this means we can say that this T inverse is equal to, you have a S, and similar fashion we try to find that we try to show that S inverse is equal to, we have in this form. So S inverse can be written as S inverse of identity of a U. This can be written in the form, and then we can S the map from this. So we can say that this S inverse ST IU is equal to ST is equal to, you have I of U, and we have a T of S is equal to identity of a V. We using so S inverse S, then S inverse. This SS inverse is equal to, because S is a map from, you have a V to U. So S inverse is a map from U to V. T from, you have a U to V. T inverse is a map from V to U. So SS inverse is equal to, you have a I of a V. So this is identity of a V, and identity of a V is equal to T, and then we can say that clearly is equal to T. So this means we can say that S inverse is also is equal to T. So ultimately what we have to show that, we show that if T is T inverse is equal to S, and S is equal to S inverse is equal to T. If we have ST is equal to identity and TS is equal to identity, then ST is equal to U and T of S is equal to identity of a V, then this result is hold true in this case. So if we have T is any non-singular map, then we clearly know that the inverse of this linear transformation is exists. So by if T is a non-singular map, then ST is identity and TS is also identity map, and also S is equal to T inverse and T is equal to S inverse. This also hold by the using the proper definition of this inverse of a function or inverse of a elements of a inverse. We know that the inverse of element, we can say that A composition B is equal to identity is equal to B composition A. Then we can say that A is the inverse of a B or B is the inverse of a. In a similar fashion, we can show that here linear transformation S composition T is equal to identity and T composition S is also identity. Then S is equal to T inverse and T is also equal to the S inverse. Okay, so now I just complete the proof of this result. Now I have to stop today's class here at this theorem, and in the next class we continue some more related results for the composition of a linear transformation. Okay, thank you very much.